And last week we discussed on interrupt. It's a very important topic, and even the tutorials. I hope that you guys take some effort to go through, even though many of you are busy. That's a very important topic. Reason why is because all sorts of questions can actually come out, and I cannot predict what kind of question will come out. But if you guys do not know the concept well, no matter what type of question come out, you will not be able to answer. All right. So I hope that take some effort to actually go through the lectures and the tutorials. It'll be very meaningful for you. And also the other topics. Okay. So as we go through the ending, more programming type of questions will be covered. I hope that you guys take the effort. All right. And today we're going to discuss. We had a preliminary discussion on the assembly language. Okay. So a quick quiz. Okay, a quick quiz. Any one of you here, right? Can you give me maybe just text me, all right? Can you give me one example of an arithmetic type of assembly language instruction set? Just one, okay? Anybody can text me. If just one example of an arithmetic type of it's not MIPS, all right? An example of arithmetic type of instruction set would be addition, okay, subtraction. So these are assembly language, okay? Assembly language. We're not talking about C, talking about assembly language. Now, what about an example of instructions that affect the flow of the program? One example of assembly language instruction that affects the flow. SVB. Maybe it's not in my radar. I will check the book, but a very typical classic example would be jump, JMP. Okay. So another question: how many types or category of assembly language instruction sets are there? Okay. This is a definitive answer. Anyone can text me. How many types of okay, there are 3 categories. Good. Okay. So there are instruction sets that that has to do with transfer of data. Example is move. And then there is example of arithmetic type. Okay. Logic or arithmetic type. Example is subtract, or, and these are what we call the arithmetic type. And the third one is the instruction sets that affect the flow of the program. Okay, very important, because we realize that in the assembly language there is no such thing as if else or whatever. We need this kind of program, this kind of instruction sets to help us to affect the flow of the program. Let's say, for example, JMP and Z. Okay, jump if not 0. Then you say that it will jump to certain parts of the program if the 0 flag is 0. Okay, so still remember the status register. You have a lot of flags. Okay, you have carry flag, 0 flag, and all this kind of flag. Okay, so this jump not equals to J, M, P, and Z will look specifically into the 0 flag in the status register. Okay, so I think we will discuss more on this revision questions as we go through the end. We are about to finish the topic of discussion. Okay, so this is an introductory course on the computation, memories. Okay, on the how the computer work, status register, and stack pointers, and all these kind of things. And now we've come to interrupt. We've also studied a bit of interrupt. Now we've come to this topic, assembly. So assembly will break into two parts. This is the first part. We're going to discuss more in depth of whatever that we did earlier. Not much is covered earlier. You guys have a rough idea of this assembly. Okay. Another thing I just like to recall from our lectures: assembly It's basically to enable the human to understand the language better. Okay, it's just one step more complex than the higher level compared to the instruction sets, the machine language instruction sets. Because human, we are not very good with understanding numbers. We cannot let's say for example, 0A B1, what does it mean? Okay, we are very bad with understanding all these kind of numbers. So it's better for us to convert all these kind of numbers into something slightly higher level, which we call assembly language. Okay, you want to go higher level more, okay, more near to languages that we humans understand. You okay, your compiler does this wonderful thing, write a program in C. C is basically a human language, okay? It's a human language. You write the code in C, just like what you're doing in the lab. Converted the two types, convert straight into machine language, or you convert into an immediate assembly language. Either way, all right? But assembly language is definitely lower level compared to C. We go slightly more in depth today, all right? Your connection isn't so good to share applications right now. Okay, I do not know why my connections are not good. Okay, the system is actually blaming my internet connection not so good, but I'm actually using a Unify, so should not be an issue. Okay. Okay, I've been talking for 5 minutes, sir. Nobody told me there's no voice. Okay, so I'll just repeat whatever that I said. The internet is not very stable today. I do not know why. Can you hear me? Every one of you, can you hear me? Okay. Actually, I've been talking. I've been talking for 10 minutes. Nobody told me anything. All right. So let's take this example. Okay, let's take this example. Uh, let's take this example. This is a C programming example. You have an LED, okay, connected to port 1 of 0. Okay. Now let's see what's the difference between a C programming and assembly language. Okay. In C programming, we say that we seldom deal with the hardware. It means to say that we program in C, but in the program itself, you don't see a lot of register stuff, right? For example, in assembly language, you deal with R2, R3. You said move R2, R3 means to say that you move the content of R2 into R3. Okay, but when you're dealing with C programming, you normally don't see a lot of all these kind of things. Okay, there are caveats. Okay, let's say for example, P2 out is a type of register. Okay, you only deal with very high level stuff in C programming, whereas all the low level stuff are actually done for you using the IDE. The IDE does all these allocations for you. You don't deal with low level hardware stuff. Okay, so but in assembly language, you deal with the hardware stuff. Okay, you deal with R2, you deal with R3, you deal with R4. All these are multi-purpose registers. You put values, you take out values, you do everything manually. Okay, so in short, C programming is basically like you can equate it like an auto car. Okay, in assembly language is like a manual car. Okay, you need to shift the gear, whereas in C programming, a lot of things are automated for you. All right, now P10. Okay, how would you set the P10? Okay, you would actually set the P10 manually. All right. In C, okay, you will set it as 0x01. Bear in mind that if you refer back to my tutorials, okay, this is a bit masking for set. Okay, bit masking set the last bit. Okay, bit 0. Okay, pin 0. So you set this pin 0 as an output. The rest you don't care. Okay, if the existing pin number 7 is an output, you're not going to affect that. Okay, so this is what we call the bit masking. I've been discussing this a lot of times. Okay, and take a look at this. Take a look at this. This is basically a delay. All right, the delay that's introduced. Maybe you buy an Arduino or whatever. You have a short wiring code. You call it a pulse for 1 or 2 seconds. Okay, but behind that library, basically it's a very someone actually wrote something like this for even for the Arduino. Okay, it's a function, but inside that function is basically something like this. Now 50,000. Okay, 50,000. This is the delay. 50,000. Now how would you do to actually make the LED blink faster? Something to do with your lab. All right. Before that, this is a bit masking toggle. Okay, means to say that whatever the existing value for the bit pin number 0, okay, you toggle. So if the existing is 1, you toggle it to 0. If it's 0, you toggle it to 1. So you keep on toggling. Okay, now this is C. We want to show you how would you actually do it in assembly language. Then you will find that you begin to appreciate that a lot of things are actually automated for you in the C programming. A short quiz. Okay, can anyone tell me what would you do? This could be a very well an exam question. What would you do to make the LED blink 5 times faster? Okay, can you tell me from the chat room what would you do to make the LED blink 5 times faster? Okay, have a look at this for 1 second. Now, what would you do to make the LED blink 5 times faster? Assume that this is a question. Anyone can answer me? Anyone? Yes. Okay. I, you divide by 5. All right. You reduce I 5 times less. So very good. At least I know that some of you are actually competent. Not You know what happens to the codes. So it's very important to be able to read code. Now, how would you know that you're ready for exam? If you read codes from the lecture slides you don't understand, means to say that you need to study more. All right. So you will repeat, okay, and this is the version in C programming. We want to bring you to how would you actually do it in assembly language. Okay, so C programming, it's a very high level language. Compiler does everything for you, and you will compile it into hex machine language, which shows debugging present machine language to users. Now, if you write the program in C, what you did in the previous slide, okay, it will compile it into a bunch of binary language. Okay, this is what you will see. I think in your IAR IDE, this is what you see. Means to say that all these numbers are basically instructions that were converted from C to binary machine language. There are several systems. Some have intermediate, some compile it to assembly, then further to machine language. But what you see in your memory are basically these instruction sets. Okay, this is what that is actually being saved in your memory. So computation cycles, CPU, will actually extract this information one by one that's being converted from C to your machine language. Okay. So instructions for the MSP consists of 1, 2, or 3 16-bit words leading to instruction words. Okay, so in short, it means that it's basically explaining to you that the instructions consist of different lengths of words. It could be a byte, it could be a word. We're going to look into this, don't worry. The first step towards a friendlier syntax is to use assembly language. So this is the reason why we, from binary, okay, we want one step that is more friendly to use, that is assembly language. So if we just read assembly language, we just read this binary codes, like for example this one, you'll never be able to make sense. Okay, but if you write in C, you don't deal with the hardware. You need to rely on the IDE to optimize the codes. So what if the IDE is not really optimized and you really want to optimize it to a very high level code? Okay, so the IDE might have unnecessary loops, convert into unnecessary loops. You want it to be optimal, you would actually try to program it in assembly. Okay. Now this is the what you would see in the assembly language. Now let's see if we can make sense of this. All right. So jump not equals 0. Jump 0 is the exact same code that you find blinking the LED, and okay. So this is the example of the LED blinking. Okay, this is in C. This is in C. Very much understandable. Some of you can even control how fast the LED blinks, and you have this value 50,000. Okay, let's see if there is this 50,000. If we can find this value 50,000 in the in this code. Okay, probably there are, but it's very difficult to find. And if you look at this, okay, so this is the P1 dir register to control whether that particular bit it's an input or output. Can you see? Okay, so this one, basically this one is the P1 direction. This line, P1 direction line. Okay, P1 direction line. So is in C is easy. Okay, so this is P1 direction. Can we find the 50,000? Okay. Okay, this value, can anyone find the 50,000? Okay, you cannot find, means to say that you're not still very good with assembly. Convert this C350 into binary. What do you find? Okay, into integer form. Okay, I think this is the 50,000 that you find, because it decrements. It decrements means to say that this is counting. Okay, so I can deduce that this value is 50,000. Okay, it will deduce until it will continue to reduce until the zero flag is affected. Okay, when the zero flag is affected, it will jump into this location. Okay, and then it will continue to jump. So you can see that assembly, it's much difficult to understand. That's why for introductory course, we ask you guys to write programs in C, but we also need you to understand a bit about the assembly. Okay, so you can see, try to understand, put it side by side, then you'll be able to understand. This is the 50,000, and this is the P1 out register. All right, and jump not equals to 0, because if let's say it keeps on decreasing, after counting 50,000, the zero flag will be set. When the zero flag is set, it will jump into this location. Okay, so this is the assembly version. This is the machine language version. All right. The basic format of MSP 430 instruction contains, these are the two important components. One is the function itself, and one is the operand itself. The mnemonic is basically the function itself. So when you say move R2, R3, okay, the move is the mnemonic, and the operands are basically the R2, R3. Okay, so the mnemonics is the name given to the machine language opcode. Okay, the function itself. Okay, jump. Okay, that one is a mnemonic. Move, that one is a mnemonic. Add, XOR, those kind of these are functions. The opcode is part of the machine language code only, and mnemonics the assembly language name for the opcode. So it's just a language thing. Okay, mnemonics have a suffix .b and .w. Okay, so if let's say you want to move, okay, the content, the whole content is a 16-bit, so you will use move.w. But if you only want to affect the lower byte, okay, you use the .b. So all these mnemonics have two versions. Most of it have two versions. Okay, of course jump you don't have .b and .w lah. Okay, but for example move, okay, move.b, move.w. Okay, so move, you move the lower byte, or you move the whole higher byte and the lower byte, you call it .w. Okay, no suffix is by default equivalent to .w. Okay, so by default means that if you don't include .w, move is basically by default is actually a .b. Okay, so I repeat again this example. Instructions, for all these instructions, you have two versions. You can affect the byte, or you can affect the lower byte only, or you can affect the higher byte and the lower byte. If you want to affect the higher byte and the lower byte, it's .w. Lower byte only is .b. And by default, they are all .b. Operands are written in MSP addressing mode, usually called source destination. So this logic, you have two operands. Okay, operands means the destination. Let's say, for example, move R2, R3. R2 and R3 are the operands. The mnemonics are move. Okay, so you can simplify. You can say that move is basically a function, and the operands are R2, R3. Okay, the source and the destination. One is the source, the other is the destination. Only call instructions without operand is written. All other zero operands instructions are emulated. Okay. Okay, this is an example of you add. Now this example, you add a lot of for labels. Okay, these are what we call labels. So that when you jump, okay, for example, when you jump, now this one is jump back to jump. If jump not 0 means to say that if 0 equals to 0 equals to 0, 0 equals to reset, it will jump back to this part of the code called li, L1. So these are basically labels. We call these labels. It enables the instructions to jump to certain parts. Why? Because in assembly code, we don't have while loop, or we do not have if else or whatever. We need to rely on labels to help us do programming. Okay, so C programming is not something that was invented 400 years ago. Okay, in fact, C programming is actually quite recent. C++ is only in the late 90s they invented C++ programming. So before that, okay, you program using this method, okay, where you have a lot of labels. Assembly language has been around much longer than C programming. Okay, so the initial concept was using labels. Okay, let's say for example, it's a counter. Okay, you this is basically the codes, the exact codes for playing around with the LED. So just now the delay, okay, is basically in numbers. You can see the delay is basically in numbers. Okay, this value, convert it into integer, you will get 50,000. Put it into this, then you decrease. But in this code, more function is given. Okay, you can define it, the delay, as 50,000. So basically you can make sense of the delay. You know that this delay equate to 50,000. It's easier to understand the code. Okay, so delay, you jump. Okay, it's basically the same thing as we see just now, but now you have, it's more readable because you have labels. Okay, so these labels allow you to understand the code better. Check it out first. Okay, so of course this line is basically to stop the watchdog timer. Why we need to stop the watchdog timer? If we don't stop the watchdog timer, your embedded system will need to be serviced every how many cycles of instruction. If you don't service it, it will go to reset. Okay, that's why you need to go to reset the watchdog timer, stop the watchdog timer. Sorry. So take a look at this 001. This is basically the P1 direction. Okay, P1 direction. So it includes the library, so that the content of P1 direction is stated as address of P1 direction. Whereas in the code, that very difficult to understand. You know that this is basically P1 direction. Okay, this is P1 direction. But if you include the library, then it's easier to actually understand. Okay, it's the same code as what we see just now. It's just that right now it's easier to understand. Okay, where the delay, it becomes a number. But you can after this lecture, convert this into an integer, should be equals to 50,000. If it doesn't equate to 50,000, please send me a text. I don't have a calculator with me to calculate. It's the same code, except that now it's easier to understand. Okay, now there's a lot of if you want to convert C into hex code, there are okay, if you want to convert C into hex code, there are a couple of ways. There are a lot of variances, but to convert assembly to hex code, the variances are even lesser. All right, so it's basically straightforward from assembly to hex code. Okay, now look at this. Okay, now we're going to teach you guys what are these. What are these? We already know that these are called mnemonics. Okay, and these are called operands. Okay, so definitely in the code you need something called commands, because if not, your code will be very difficult to understand. And these are basically what we call labels. All right, so label, mnemonics, operands means to say that the source, the destination, and these are the commands. Okay, anything after this semicolon is considered a command. All right, so you can have command, label, symbolic, okay, whatever. Okay, this repetitive or whatever that to you. Okay, sometimes you want to find out this instruction set. Where is this instruction set? Where do I locate this instruction set? So when you have a assembly code, okay, you write the assembly code, then you compile. You will have this thing called the list file. The list file is very useful because it tells you every single direction, okay, every single instruction, where is the location.
So you have this is a text file. You have this, and you can locate, okay, this instruction is in F80A in the memory. It's very useful because sometimes you want to know, okay, where is this instruction set? Go to where, you know, this instruction. So this is basically manual. Okay, you're able to understand the code more comprehensively. All right. Directives are for assemblies and will not translate into machine. They serve to organize the program, create labels and symbolic names. Okay, so what's being compiled is basically the instructions, mnemonics, and basically the operands. But the directives, okay, let's say for example the labels and etc., they help us to understand the code better. Now have a look at this. This is with a lot of directives. You have you have LED. All these are directives. Labels are directives. These are all directives. Compare with this. All right, very difficult to understand because this one you don't have directives. Okay, so it's very difficult to understand. Yet this one works. All right. Similarly, it works as well as it's exactly the same as this one. Okay, but with this, it's easy to understand because now you have commands, you have labels, and you have directives, the hash include and all these kind of things. Okay, so in short, the directives are only for the assembler, will not translate into machine code. If you look at this hex code, okay, 4031, then it ends with 3FF9. Okay, 4031 FF9. Exactly the same thing, just that this guy who wrote this part of the code are very familiar, and he does not need all this kind of help from the directives. Okay, so he can basically code, he can understand all these kind of numbers. All right. Anything after a line, including semicolon, is command. Command very important. If you go to the industry, command is very important because you don't code everything by yourself. You need to work in a team. Okay, that's why certain companies have their own way of writing commands. Okay, they might include a date or whatever to update the instruction sets or whatever. So this is important. Is a practice. How you do the commands is very important. Okay, although at this stage of learning it might not be so important for you, but when you work in a team, command become very important. Just now we talk about symbolic names. Okay, 50,000. Okay, is basically we cannot understand, convert 50,000 into hex. It's very difficult to understand. So we have expressions like equate. Okay, that helps us to understand. Or delay equals to 50,000. I just minus off the value of delay because delay is easier to understand compared to 50,000 or in hex form. All right. Labels, okay. Labels allow you to, again, labels allow you to jump into certain part of the program. Okay, because why we need label is because labels will not be compiled, okay, into hex code, but labels allow you to go from line to line. Okay, bear in mind that just now we have lists. Okay, we have lists. We have this. We know this instruction is in the list. Okay, now if we do not have labels, can we continue to run the program? The answer is yes, provided we have this list. We know where is this instruction. If jump not equal to 0, go to jump to this part. We know that this is the location for this machine language and for this instruction set. But label make our life much more easier. Okay, because we can understand what is L1, what is main, what is program. You know, so labels are very important for us to write proper codes. We don't need to memorize the location of every single instruction set, but you do have a list file. Okay, and where the list file you can jump to certain locations. Okay. There are a couple of directives. Okay, these are the things that are important for the user to code. Define, include. Okay, just now we define delay as 50,000. So it's very easy to understand. Oh, delay is basically a number of 50,000. You want to make it faster, you divide by 4, etc., etc. Okay, so when you define the value to something, it's easy to understand the code, right? So this is the format. H include, you include the library and so on and so forth. Okay. Without all this, your code can still work. In fact, when you compile it, it will be exactly the same machine language hex file, but this allows you to understand the code and write it in a much better way. The ORG means to say that the origin, okay, you can define, okay, where the physical address, your program location will point to store to the next. Okay, so if you know that your program starts at this memory, okay, the instruction set starts at this, you can origin it at a very specific location of the memory. So very important. To simplify readability and comprehension, okay, symbolic names. Good example is the 50,000 that we just go through. Okay, we do not understand the delay. Okay, so if you read the code, okay, you pass the code to another friend and continue to develop, your friend might find it easier to continue your work if everything is properly defined. Delay is 50,000. So if his boss asks him change the LED to blink much faster, he can take the delay and he can just reduce it to 10,000. Okay, so for him, it's easier to understand that way. All right. Watchdog timer. Okay, so watchdog timer is basically a word. A word means to say that higher byte, lower byte. Now, a bit of quiz. Just now we went through instruction sets by default. Are they .w or are they .b? Okay, by default they are .b. So if you move or do any instructions by default, if you don't define it as .w, it will treat it as a byte. All right, a byte. It only affects the lower byte. Now this is the watchdog timer register. The top part is only important for if you want to write, you have to put a 5A at the top. Okay, so this is 5A means 5A. 5 is 1 0 0 1 0 1. Okay, so you can convert it into binary. If you want to write something to this register, you have to define the top byte as 5A. And these are the various, just like your status register, these are the registers that are important for different things. So if you want to select and the interrupt age for the non-maskable interrupt, then you need to define this bit MIES as either 0 or 1. Okay, you define it as 1. The interrupt age for the non-maskable interrupt is equals to 1. So it's rise or fall. Okay. Let's take another example. Select. Okay. So this bit either 0 or 1. Okay. If you put this as 0, that means the source of the clock is the submaster clock. But if you put as 1, the clock will select auxiliary clock as the source of the clock. Why do you need clock? It will count from certain value to certain value. If you do not service or reset the flag, your embedded system will go into reset mode. Okay, so this is what they do to, they call it the watchdog. Means to say that sometimes due to certain reasons, your program hang. Okay, now when you go to lab, okay, your PC hang. Okay, so who does the reset for you? You're not in the campus, so Dr. Filbert will or me, we will go to the lab and we will push the reset button. Okay, now what happens if we are not at the site? Okay, if you have an embedded system that is in somewhere in the jungle or whatever, if you do not have a watchdog timer to automatically reset when something happens or hang or whatever, your embedded system will just remain hang. There's no indication that it hangs. Okay, so it just remain hang and nobody will be able to find out something wrong. But watchdog timer is an automated way to reset if the program is not responding. Okay, so so this is the watchdog timer. Please go back and just understand this 8 bits are important. These 8 bits are important. So the higher 8 bit is, you only need to understand 5A something. Okay, so it's 5A plus 80, 80 or whatever. So the top part, if you want to write to this register, you need to assign it as 5A. Okay, so use the table. Okay, use table. For example, if WDP is 5A00 and to make it whole is 80, so you need to have A80. Okay, 5A80. So you need to do something like this in order to write to this register. Top part need to be 5A, and then it depends on the number that you want to assign here. The register 5A plus something, the value. All right. So watchdog timer is important for you to automate the reset of the embedded system. Something happens to the embedded system, it will auto reset. Okay, if question asks you, what happens to this code? Okay, what happens to this? What happens to this code if I remove line number 10? Now this is a valid question. It has come out before. What happens if I remove this part of the code? Okay, what will happen? It means if you remove this part of the code, watchdog timer will kick in. Okay, and if you don't service it in time, the whole embedded system will go into reset mode. Okay. So watchdog timer, if you're not using it, bring it to reset. Again, if you're in a developing embedded system for data logging for rural area, this is very important. Okay. For a group of bits referred to as a symbolic, there are two general conventions. One can leave reader. Okay, there's not much stuff. This is just reading lah. Okay, you can read yourself. Okay, so in the MSP products, okay, when you include the library, there are certain ways that we can define a value. Let's say, for example, WTDIS0 actually means 00, DIS1 it means 01, DIS2 it means 02, DIS3 it means 03. It's the same thing as bit 0, bit 1, bit 2, bit 3, bit 4. Now the bit, if you use this kind of system outside of MSP, nobody will be able to understand what does bit 0 actually means. But bit 0 actually means 000, 001. Okay, is useful for bit masking. Okay, again, I want to repeat, these are symbolic constants that are in the library. Okay, bit 0 means 000, 001. This is bit 0. Okay, bit 1 means something. Okay, now these are constants associated with this name, because it's very common to use this watchdog source. Okay, so you want to have the watchdog. If you want to take it from the auxiliary clock or the master clock, you divide it by such a value to make it slower or faster the count. You take out this value. Okay, you take out this value. So WTDIS actually means 00. WTDIS1 means 01, 02, and 03, and so on and so forth. Because it's easier to understand this symbolic value than the value itself. Okay, so you know that this is common. Okay, when we do bit masking, let's say for example, bit 0 means the first bit. Okay, so if we include the library, this symbolic constant help us to understand the program better. All right. Of course, labels is to, I already explained this again and again. If you don't understand, you can ask me. All right. Labels allow you to jump from which section of the programs, because I already told you guys, there's no while, there's no for or if or whatever. There's no such instructions in assembly. That's why you need to use labels. Again, if you know the instruction, the location of the instruction based on the list file, you can actually do without labels. But labels allow you to jump from different locations without memorizing the location of the instruction. And then you have stuff like reset, initial, start. All these are basically they are a form of labels. Okay, so if let's say is it reset if not equals to 0, the location jump to reset. Okay, so the MSP will jump to reset mode, the reset address, initialize address, or the start address. Okay, so all these addresses, all these labels, they represent an address in the program. Okay, just like this. All right, just like this. All right, so these are all labels. These are all labels. We know that reset is actually at this address. Okay, we know that L1, we do not know where is L1. Basically, you define L1, and I think uh, the uh, the IDE will find a location in L1. So it's automated. You don't have to memorize the location of L1. So it will just identify where's the location of this line, and it will jump to the location of this line. We have the list file. If you do not want to do this, you can do so without the labels, but it's very troublesome, very difficult to understand. Okay. So again, reset is just a label, but it's a very is something like a reserved word. You always reserve this reset to certain location. You can have reset, initialize, start. All these are basically normally reserved words, but they are labels, but they are reserved labels. All right. So reset, initialize, start, they are nothing but labels. Okay, but normally you don't simply use this reset or initialize. They are normally reserved for reset address, initialize, start of the program, or so forth and so on and so forth. What if I want to repeat the program again and again and again? Okay, in the beginning of the C program, you have while loop, forever while loop. Okay, what if you want to continuously repeat the program and again? You say jump $sign. Okay, so the program will keep on repeat again and again and again. If you have, after you execute the program, you write the program, then you end with jump $sign. So the program will keep on looping. Again, why do we use jump $sign? Because we don't have a while loop. We don't have a while loop, we cannot use forever while. So we use jump $sign. So it's equivalent. All right. Okay. Stack pointer is usually initialized. Okay. Yep. So it's usually initialized after the RAM. Okay. So if the RAM is here, ends here, you normally assign the stack pointer after the RAM. Okay, so this is where you save all your codes and stuff like that. Then after you save all your codes, you initialize the stack pointer. All right, so this is a standard practice. You always start with this, move this value to this location. This is a register that we just learned, the watchdog timer. So you turn off the watchdog timer by taking out this line. Okay, question might ask you, what does this line do? Stop the watchdog timer. Okay, again, I repeat one more time. What does this line do? It stops the watchdog timer. Okay, this one. Now, by now, I do not know before this whether you've learned of pull up and pull down configuration. I hope you've done something on this. Okay, so by default, okay, pull up configuration means if you don't touch anything to do with this pin, it will be 5 volts. This pin normally is 5 volts, but in the pull down configuration, this one will be normally it's 0 volt. Okay, so you might decide, okay, if the signal nothing is applied to the signal, is a pull down configuration. But the thing with embedded system is you can have an auto configuration. Still remember PXREN that I asked you to investigate yourself. You give a value to PXREN, it will internally set it as pull up or pull down. Again, I repeat, if you don't want to do it using circuit, this is a pull up configuration. Pull down configuration in your embedded system is configurable using the PXREN register. Okay, PX REN. So if you want to affect the port 1, it's P1 REN, port 2 P2 REN. So the P2 REN affects the pin. You can configure it as a pull up or pull down configuration. It makes a lot of difference when you are transmitting signal. Okay. Okay, the next slide show an absolute source file for the LED is called okay, let's have a look at this. Can I zoom in? Okay, I hope that you can see, but later I'm going to upload into this YouTube. You can actually have a look. This is how they do LED blinking. Okay, and you will have this section here. If you observe, this is an interrupt. Okay, so this is how you define an interrupt. If anything happen to this, is actually assigning this address FFFE as a reset address. So when you say reset, okay, it's actually initializing. Anything happen, it will have an interrupt procedure to go to reset. Okay, so that is actually what it means. The top part is basically very similar to the blinking LED that we just had. So these are the explaining the different, all these are documentations, the commands, the constant declarations. This is the what you configure the code, and this is basically allocating the reset vector. Okay, it means to say anything happens, you move to reset, and reset is basically FFFE. You can define more vectors, all right, as you wish, but this is the common. If the question asks you what does this part do, basically is you're allocating the reset label to this address. This is a reset address. So anything, the computation cycles, fetch, execute, compile, fetch, execute, and all this, the 3 states, it always start with FFFE. Okay, so anything happens, it will go to the E. Okay, so I hope that after this lecture, you'll be able to understand this section of the code better. All right, labels, mnemonics, operands, and these are commands. Can you operate without the labels? You can, but you need to know the location of the instruction. The AND directive is now talking about this part. Okay, so anything happen, you can assign it this word reset with this address, but you have to end it with N. Okay, this is what it means, that you can actually stands for define world. Okay, so I think this is just reading, but you have to end the directive. Okay, end directive. Okay, needed to finish the source file, since the assembly does not read anything else after this directive. So it's basically you want to define this as a reset vector. You need to end it with N. Okay. Reset vector is always 0 FFFE. Okay, again, this is a reset vector is always defined as FFFE. So when you set reset vector, okay, you can go to this reset vector. Okay, it's always this reset vector word actually always means FFFE, just like how bit 0 or bit 1 or bit 2, they have certain values associated with that reserved word. So reset vector is FFFE, is reserved for this purpose. All right. Sometimes, why do you decide to use assembly language? Why do you take all the effort to learn this? Lower power consumption, least memory usage, faster operation. I would say that if you want optimality, you have to code in assembly language. If you want convenience, code in C. All right. So I think that's all for this week's lecture. Try to read chapter 4. If you don't read it in depth, at least go through one time. Okay, you have a better understanding of assembly language. Okay, today at least you know the blinking LED, which section is for what, and all these different purposes. Okay, so I think that's all for the lectures. I will come up with the tutorials. We will be heading to revision very soon. Before we go for revision, please revisit all the lectures that we have covered so far. Each week there is a special topic that we discuss. So I think that's all for this week. Thank you very much. Okay, see you guys.